Don't forget, today, today in the math club, we have Dr. Norton coming, and he's going to tell us about his adventures as an expert witness. You know, he's a statistics guy, and it should be quite fascinating. So I put that on my calendar. The last time when I left off, I gave you an example of, we talked about valuation domains, and I gave you some examples of Noetherian valuation domains, polynomial rings over the field, Z localized at a non-zero prime ideal. I gave you an example of this one, I guess. Set of polynomials. I use the term loosely. Q are positive rationals, and AI is in the field. And if we let this come R and V equal R localized to M, where M is the ideal generated by the set X alpha, where alpha is bigger than 0, then V was valuation domain, and it turned out that any non-zero element was in the form X to the alpha times a unit, right? Where alpha is greater than or equal to 0. If it equals 0, then it's a unit. If it's greater than 0, it's a non-unit. And this actually shows that it's valuation domain, because if you compare any two non-zero elements, whichever one has the smaller alpha is the one that divides the other. Here's another kind of valuation domain. And I'm going to build this. This is going to be what I call two-dimensional. I'll try to explain what I mean by that. Well, what I mean is the prime ideal stacking, but it might be clear how you can build this even bigger. This is an example we looked at before in a different context. So take a field. So notice that this is an overring of a polynomial ring over field two variables, right? So notice everything in here that I need to generate is of course a rational function. So this is contained in the rational functions in two variables. Now, if you look at the ideal M, is generated by all these rational functions that I have here. This is a maximal ideal, because if you look at R mod M, you get a field. So this is a maximal. This is a big boy. Now this one I think requires, this one's a little bit easier to kind of wrap your head around. If you look at Rm, so this is the set of, let's say, F over G, where F and G are in R, and the constant term of G not zero. That is, it's everything that's outside of this maximal ideal, right? Because everything in here is a linear combination of products of these rational functions. And so if you use a constant that's not in there, then that's outside of the maximal ideal. So I want to discuss what a typical element, what can we reduce this to? So suppose let's look at elements. So for example, you might have an element. So I'm gonna do a couple of examples and then we'll try to get the general form, right? So you might have something that looks like this. Regular polynomial next, that's an element in there, right? I'm gonna keep the constant term not zero, because if the constant, I'm gonna keep the constant term zero, because if the constant term is not zero, then this is just a unit. Notice this is x. So this is x times a unit, because this thing in the in V is a localization, right? It's a unit localization. Okay, we could do the same thing with y here as well. But what happens if you mix them, right? What if you have something like let's do something more exotic. What about this one? This one's also x, believe it or not. Right? Again. Because notice. Never thought I'd pull that off, did you? Right? But notice I have a y cubed over x that allows me to do this. And notice this is a unit. Right? And so we might have something like this. How about something a little bit more general? Notice I can have large powers of x in the bottom. So I could have x plus y over x to the 5 plus x4 y cubed plus y squared over and actually, you know what, for this one, this is just x again. I'm gonna erase this one. Let's just do this. What can you pull out of this? Yeah, I guess it's probably, so what I'm looking for is this is supposed to be, let me clarify, this is y cubed, I guess.
What happened if we pull off the first one?
That's exactly right. Certainly. And this gives me a y squared over x. Oops. It's 9, I guess. Right, that's gonna be, that should be a y squared too. There we go, so it should be y cubed, well, yeah, that's right. And this should be y over x, should be y. And this should be y to the 6th over x. If I agree with it. These are all elements in the range, so this is y over x5. This is partly where valuation, when we call these valuation domains, where this comes from. Notice that in all three of these examples, there was sort of a lowest power that I could pull out. Here it was x. Here it was x again. And here, the lowest power seemed to be y over x to the fifth. How is this lowest power determined? So I'm gonna make the following claim.
And just to clarify, are you trying to represent elements of Rm here or elements of?
Yes,
Rm?
elements of Rm in the localization, right? And that's how I get away with that, because I pull that out, and it is true that R over M can be written F over G, where you can put stuff like this in the denominator, but that just muddies the water. It's just still y over x to 5 times some unit, right? Yes, these are elements when I'm doing this computation, and then I say, actually, the first part of the computation where I pull this out, that can be thought of as taking place in R with the example I've got. But when I say unit here, I mean in the localization.
Right, because you don't have anything complicated in the denominators here. Like, you don't have anything added in the denominators. Are you saying you can expand anything out of that form into a?
Yeah, well, there's never anything in the denominators except for powers of x and units. Right? So in the localization, what happens is, if you write this rational function, whatever it is in the localization, the only thing that comes in the denominators out of this are just powers of x, right? And then when you localize, you can also put in things of this kind of form. Non-zero constants here. But I can just call them. It's kind of cheating a little bit. But I can just call that a unit, right, in the localization. You're right, this is not a unit in the original ring, but once you turn everything outside of that maximal ideal into a unit, it's acceptable in the denominator. Right? So I'm going to make the following claim. Any non-zero element of Rm one is one of the following. N great than equal to 0, and U a unit, or y to the k, u to the n, sorry, x to the m, u, where k is greater than or equal to 1, m an integer, and u a unit. And in fact, for this one here, you might think of this as y to the 0 times x to the n, right? So with the zero power on y, only positive exponents of x are acceptable. If y has an exponent of 1 or higher, you can go crazy on the exponents. They can be positive or negative. Now, let's suppose, and basically the proof of this is up to a unit, every element of Rm you might have powers of x only. you have a polynomial on X, if A0 is not 0, then this is a unit. Right? If not, or if A0 equals 0, then write this in the form AK XK AN XN, which is with AK not 0, and of course you pull next to the K out. And this is a unit in RM. So there's one of my claimed forms right here. Now, what happens if there's some Y's in there, if you will? More generally, you might expect an element to look like this. A polynomial over only an X plus the sum of Y Ki over X. Well, prices, right? X Mi, where to capital M or capital M. So in general, you might expect an element up to a unit. So notice that up to a unit, I can write every element in R localized M as something in R. Because if it's got a denominator, I can clear that denominator with a unit. So basically what I'm saying is your numerator can be chosen in R. And what does a typical element look like? Well, typical element looks like sums of products of these things. But of course, a product of a Y over X to the I is a bigger power of Y over a bigger power of XI. So it looks like this. Notice that if P to the X is not 0, then whatever the smallest power of X that you see factors out of P of X and all of this. Because you just put some extra powers of X in the denominator, right? Everybody agree with that? Yes.
That MI is integer or not?
I'm sorry, I meant to write that down. Ki is greater than or equal to 1, and Mi is an integer. Thank you.
All right.
So if P of X is a non-zero polynomial, then take the smallest degree X and pull it out of this. It also pulls out of the second part of the sum, and it's a power of X times a unit. So again, this first form. If P of X is 0, then this is Y to A over X to B times unit. And how do I know what the power is? Where A is minimal among all Ki and among all such Y to the A, X to the Mi, B is the I always get this confused. Well, it is minimal. So in other words, if you have something like this, now this is not a polynomial next, so what you do is you choose the minimal power y that I see. And in this case, my minimal power is 1. So this should be y. And then the minimal power of x is x to the minus 3. So this should be x squared plus 1 plus y squared, x to the 14 plus y cubed over, well, that should be x to the, what, 89? Yeah, like that. And again, I have a unit, and these elements are all still on the ring, right? And so this is why this is valuation domain. What you're doing is in these forms here, I'm gonna try to convince you that any two elements are comparable, that is, one of them divides the other. Yes,
So here, why we have to pull up the second one and we're gonna pull up the first one in order to obtain a unit.
why can't you pull out this one?
Yeah,
Because then if you pulled out this one, you would have y over x, 1 plus agreed?
right.
This element's not in the range. There is no 1 over x squared. And that's your problem right there. Right? Whereas there is an x squared, there's no 1 over x squared. That's why you have to do, and that's, so what you're doing basically, how many of you have ever heard of lexicographic ordering? Right. That's what how many of you have ever been to the library? Raise your hand, right? How do you look up something in the card catalog, right? Say by author. So you're looking up Kuykendall, right? Okay, C first. So you go to the C's, and then to find out further where it is, you compare the second letter. That's exactly what you're doing. If you compare two elements, x to the a, u, x to the b, b, then compare a and b. So if a is less than or equal to b, then this thing divides that, right? What if you compare x to the a, u, and y to the k, x to the b, b? This one always divides that one, right? Y to the k, here k is greater than or equal to 1. Y to the k, x to the b. And the quotient is, of course, y to the k, x b minus a, du inverse. Right? And this is all hunky-dory because notice the k stays the same, it's bigger than 1. So I don't care what b minus a is, I'm allowed any power of the x as long as there's a y there to protect it. Now, the big question is how do you compare if they're both mixed, so to speak? If you have y to the k, x to the a, u, y to the l, x to the b, b. This is where you got to go to the library, right? So if K is less than L, then, Y to the K, well, let me just put it to you this way. Y to the L, X to the V, over Y to the K, X to the A, U is Y to the L minus K, X to the V minus A, VU inverse, which is in R, because L minus K is greater than or equal to 1, so this can be any power. So certainly, if K is less than L, then we get, so the smaller power apply divides the other one. What happens if it's a tie? That's right, you gotta go to the second letter, right? If K equals L, then compare A and B. If, say, A is less than B, then, or, well, actually, less than or equal to B, then Y to the L, X to the B, V, over Y to the K, X to the A, U, is Y cancels this time, and we get X to the B minus A, VU inverse. And since B is greater than or equal to A, this is known as the ring. This is a valuation ring because basically this ordering, this total ordering here gives something called valuation, we'll talk about later. You can build these things more generally. I'll just give you sort of a beginning. And then localize the appropriate maximum ideal. This one's actually three-dimensional. You actually have the zero ideal, and then sort of the ideal derivative of Z. Z is the baby, it's divisible by everything. And this is kind of interesting, because the prime ideals in here, we have zero inside, squared. Anything with Z in it will do. That's a prime ideal. Well, there, but Y over X, Y over X squared. Right. If you've got Y in an ideal, then you certainly have Z because 0 to Y is not on the ring. Notice this is kind of interesting. These are actually the only 4 prime ideals in this ring here. The 0 ideal. This is the height 1 prime ideal, which is not finitely generated. Then there's a height 2 prime ideal, which is not finitely generated. And the maximum ideal is principal. Right? This kind of situation can never happen in the theorem ring, as a matter of fact. So we'll talk about valuation. I'm sorry.
What situation never happened for that?
Well, you have, these are the only prime ideals in the ring, and they're linearly ordered, right? And in the theorem ring, even having this right here, there would have to be infinitely many maximal, or I'm sorry, infinitely many ideals between there. Okay, we will look more at this later, actually. Let me get on to talking about homomorphisms. And some basic extensions. So I like to think of extensions as a way to build new rings from old. So just for completeness, start here, definition 2, 1, or maybe it's 2, 1, 1, that's what it is. let R and S be rings. So I'm gonna give you a slightly more general definition first. A homomorphism phi from R to S is called, is a function satisfying. Spell that. Number one, phi of A plus B is phi of A plus phi of B. And let me take a moment just to emphasize that this just means an abelian group homomorphism. So of course, a homomorphism of rings has to first respect the fact that it's an abelian group. And two, phi of AB is phi of A, phi of B. And here, of course, A and B are elements of the ring R. So I will, just like if you're in group theory or beginning algebra class, there's a number of sort of adjectives that I might attach to this, right? Like I might say a monomorphism for one-to-one homomorphism. I might say, yeah, that's another one. I might say epimorphism, or I might say subjective homomorphism, or isomorphism be a bijection that is also a ring homomorphism. Here's another assumption we'll make. If R, so, and I'm gonna say a word about this, because when I first saw this convention, which is a standard convention, I was like, why, you know? There are a couple of reasons. Suppose R and S have identities. We will assume that if phi is a homomorphism, then so I'm going to assume that a homomorphism takes the identity. I always thought, is this made up, right? Why? I never like putting restrictions unless there's a good reason. There is, here's a theorem that without this assumption shows why this is true, or why this, you know, one might argue. Proposition 212. If phi is a non-zero ring homomorphism, R and S have identities, and phi from R to S is a non-zero ring homomorphism. And if S is a domain, then this must be the case, right? So if you have, of course, this doesn't make any sense to have this discussion in the first place if you don't have rings with identity. But let's suppose you have rings with identity and you have a non-zero homomorphism from R to S. then, if S is a domain, it forces phi of one to be phi of S. And, the proof of this is straightforward. Suppose right, well, this is a homomorphism, so phi phi of the identity squared is phi of the identity. This is x squared, and this is x. So I get x squared minus x is 0. Since phi is non-zero, by the way, it's fairly easy to see that if you take the identity to 0, you've got to take everything to 0, right? Then x is not 0. Therefore, x equals 1, S for emphasis. So it's as simple as that. Okay. Here's another good reason for this. So this is, I often say, and I'm gonna throw this in for this is just kind of for culture. But how many of you, I know there's some of you that are interested in category theory perhaps. I know that you've expressed an interest in this. There are some others. There's some categorical reasons why you would want this as well.
It's the integer's initial, right?
Okay, right, so, yeah. So you have these categories, and I'm not gonna really get deep into the woods on this, right? But you have the category of abelian groups, and their homomorphisms. You have the category of community of rings of identity and their morphisms. You have category of rings and their morphisms, modules and their morphisms, and so forth. Initial. An object I such that for all x in the category, there exists a unique morphism F such that F from X, right? An object is terminal as opposed to initial if
Why there's a unique morphism here such that
That's
equals to y to.
you can make a career out of turning the arrows around. If an object, let's call it P, is terminal, if for all X in the category, there exists a unique morphism next to T. So let's look at some examples. How about the category of abelian groups, say, for groups? Is there an initial object?
The zero group?
Right, the identity, if you like,
Oh,
right? Sure. Is there a terminal object?
oh, yeah.
Yeah, so the identity would be both initial and terminal, right, in the category of groups. This also works in the category of modules, right, because modules are a generalization group. Now, in the category of rings, can anybody give a terminal object? Zero ring. The zero ring is a terminal object in the category of all rings, right? It is not a terminal object in the category of commutative rings of identity. Why not? There ain't no identity, right? I mean, you could get into an argument, right? I mean, it's, so the zero is not really an object in that category. I mean, it depends on what crazy logician you argue with, but yeah. However, under our assumption where you take the identity of the identity, there is an initial object in the category of commutative rings with identity, and what would that be?
Integers.
Right. In commutative rings with identity, Z is an initial object. So at least we've got that. You don't have a terminal object. Because if S is any commutative ring one, then define phi sub S from Z into S by by the way, despite the name initial, so this homomorphism, you just take the the one element of Z to whatever the identity is here and just see where it goes. And that determines the entire homomorphism, right? Notice that this homomorphism is not necessarily one-to-one, right? Because, for example, S could be Z mod N, right? And this morphism, but there's only one morphism that takes one to one in the Z mod N. There it goes. So that's another kind of good reason, because if you force that, then you've got an initial object there. So that was my little sidestep into the world category, if you will. So let's see here. Definition. Yeah. P from R to S is a homomorphism. Then kernel phi it's a set of X and R such that phi of X is 0 is well, let me just say that this is a definition. And image of phi is the set F of R as R range C on this bar. Notice that I'm sure you've all seen, it's well known that this is an ideal of R. And it's a proper ideal actually under our assumption that one has to go to one. And the image is a subring of the target space. I'm not going to go through all of these, but and in fact, you do all those homomorphism theorems when you're in first algebra class or second one even. And the first one is sort of the king of the isomorphism theorems because the other ones kind of follow. You basically use that to prove the other ones. Theorem. Writing this down formally. If P from R to S is a homomorphism, then her phi in R is an ideal. M P in S is a subring, and R mod the ideal for phi is isomorphic. This is what is popularly known as the first isomorphism theorem. I give you a proof in the notes. I won't bore you too much with that here. So now that we have done kind of a quick, fast review over homomorphisms, and at least first isomorphism theorem, I want to talk a little bit about polynomials. It's kind of good to talk about this, since I did talk about all the category stuff. So let me kind of start off with what you're familiar with, I guess. Yeah, I guess I won't do this. I'm going to start off here with series definition. Some people might get mad at me for doing it this way, right? Because oftentimes you start with polynomials through the more fundamental construction, and you get to power series by doing something fancy, by completing a certain time. But I'm going to do this sort of backwards, sort of like we did direct sum and direct product, because as modules, that's what we're doing here, is essentially countable direct sum and countable direct product. Let R be a ring. Power series. Over R is the set of elements of form. I mean, you can think of this as just symbols. R X in R in R. Just think of this as symbols, right? I mean, the analysts are the ones that screwed this all up, going around trying to plug things in for X, right? We know we're algebras, we can only plug in zero. Actually, that's a little bit fast to lose. My apologies to the analysis people for, making fun at their expense. But for right now, yeah, these are just symbols. That's all it is, right? So I mean, it's very much like a direct product. The operations are, number one, when I add R n X n plus sum R n prime X n, this is sum R n plus R n prime. So you add it just component by component as you think you know it, and you multiply it by R n X n times R n prime X n. This is some new power series. Cn X n. Well, that's a bit of a cheat, isn't it? I guess I should tell you what Cn is, with Cn being the sum from k equals 0 to n of Rk R prime n minus k. So this is, you all are familiar with how to multiply. So basically what you're doing is you multiply this out in some giant distributive thing, and then you group all like powers and gob them together. The polynomial ring Rx is the subring of R power X, consisting of finite sums. that is Rx is the collection of sums. Okay, A equals 0 to n. Right, okay, so that's my backwards definition of polynomials from power series. And we'll talk more about what this is all about. Polynomials are incredible, just like the direct sum. So it turns out that every R module is the homomorphic image of a free module. There's an analog. If you have any ring, it's a homomorphic image of a polynomial ring in enough variables. And we'll discuss that further. Any questions? All right, y'all have a fabulous weekend. Think about coming by the math club, and other than that, I will see you all on Monday.